In business, we all say we're data-driven. We live and die by our numbers. But let's be honest, what if those numbers are lying to you? Today, we are pulling back the curtain on a discipline called Measurement Systems Analysis, or MSA. Think of it as the ultimate quality check for your data itself. By the end of this, you're going to see why this isn't just some niche statistical tool. It's absolutely non-negotiable for anyone who's serious about making decisions that actually work.
So let's just start with a really provocative question. Are your business decisions based on a lie? Now, I know that sounds dramatic, but if you can't trust the data you're using, then every single strategic choice, every big investment, is basically being built on a foundation of sand. We're not talking about rounding errors here. We're talking about a fundamental misunderstanding of what's actually happening in your own operations.
And this is really the core idea. The quality of your entire strategy is only as strong as the quality of the data holding it up. So you can think of measurement systems analysis as the structural engineering for your data. It's what makes sure your business is actually built to last.
Okay, to really diagnose this problem, you have to start with this one simple but powerful equation. Imagine something comes off your assembly line and it's out of spec. That's your total variation. Now, the first instinct is always to blame the process, right? The machine must be off. But this equation shows us there are actually two potential culprits. There's the real variation in your process, sure, but there's also the noise created by how you measure it. MSA is all about finding and silencing that measurement noise so you can stop chasing ghosts and start fixing the real problem. So here's our game plan. First, we'll talk about that variation you can't see. Then we'll deconstruct what measurement quality really means. We'll do a deep dive into its two pillars, accuracy and precision, then get into how to put it all into practice. And finally, we'll tie it all together and talk about why this is the true foundation of quality.
All right, let's dive right into our first section. We're about to expose what I like to call the hidden factory of error, that measurement variation that can silently poison your data and lead you to make some really bad calls.
And listen, this isn't just some abstract theory. It is happening in your business right now. In a factory, maybe two different operators with two different calipers get two different results on the exact same part. Or think about a call center, where every manager has their own subjective idea of what a good call sounds like. That's not just an HR problem. It means your performance data is totally unreliable. You're probably rewarding the wrong people, and your training programs are completely missing the mark. Okay, so we've seen the problem. How do we actually start to solve it in a systematic way? Well, we build a framework. Any trustworthy, high-quality measurement system is really built on two foundational pillars. If you can master these two, you're on your way from unreliable noise to data you can actually bet on. And those two pillars are accuracy and precision. And I absolutely cannot stress this enough. They are not the same thing. Accuracy is all about hitting the target, getting close to the real true value. Precision is about consistency. It's about getting the same result again and again. You can see how you can be incredibly precise with a nice tight grouping of shots, but be completely inaccurate because you're hitting the wrong part of the target. You need both. All right, let's do our first deep dive. We'll start with that first pillar, accuracy. This is all about one simple question. Are you even hitting the right target?
So what is accuracy formally? Well, it's just the gap between the true average of something and the average you're actually seeing. Let's say you have a certified weight that you know is exactly 10.00 kilograms. You measure it 10 times on your factory scale, and the average comes out to 10.05. That little 0.05 kilogram difference, that's your accuracy problem. But just saying it's inaccurate isn't helpful. That's just a symptom. To really get to the root cause, as a good consultant would, we need to break it down further. And accuracy has three distinct components: bias, linearity, and stability. Each one points to a totally different problem that needs a different fix.
First up, bias. This one's pretty easy to get. It's a consistent, systematic error. It's like that bathroom scale at home that's always 5 pounds heavy. It doesn't matter who gets on it, it's always off by the same amount in the same direction. Now think about that in a factory. If you're consistently overfilling every single container by just a tiny amount, that could add up to millions of dollars in product giveaway over a year. Next is linearity, and this is where things get a bit more subtle and, frankly, more dangerous. Linearity asks, is that bias consistent? So does that scale that's 5 pounds heavy for a 150-pound person suddenly become 10 pounds heavy for a 250-pound person? A linearity problem is a huge deal because it means your error changes depending on what you're measuring, making it really hard to predict. And the final piece of the accuracy puzzle is stability. This is all about accuracy over time. Does your system drift? You know how some old equipment needs to warm up for an hour? The measurements you take in that first hour might be totally different than the ones you take later. That's a stability problem. It tells you your process isn't robust, and that changing conditions or even just the time of day can throw everything off.
So, we've got a handle on accuracy, but hitting the bullseye on average is useless if your shots are all over the place. That brings us to our second pillar, precision. This is all about consistency and taming that random variation in your system. Now, I want you to look really closely at the definition of precision here. It's the degree to which repeated measurements show the same result. What's missing from that sentence? Any mention of the true value. And that's the key insight. Precision doesn't care if you're right or wrong. It only cares if you're wrong the same way every single time. You can be incredibly precise, but still completely inaccurate. And just like we did with accuracy, we have to deconstruct precision into its two key parts. First, you have reproducibility. This is all about the tool. Can the same person using the same tool get the same result over and over again? This tells you how much variation is just built into your equipment. Then you have reproducibility. This is all about the people. Can different people get the same result? This isolates the variation that comes from human factors like training or technique.
Okay, the theory is done. We've built the whole framework. We get accuracy, we get precision, we get all the little subcomponents. So now the big question, how do we make this actionable? How do you actually do a measurement systems analysis?
Well, hold on. Before you can even think about studying your system, you have to talk about the absolute foundation of all of this, calibration. This is basically step 0. It's where you check your measurement tool against a known certified standard. Think of it like setting your watch to the official time. If you don't do this, you have no way of knowing if you're accurate or not. And it's not a one-and-done thing. Calibration is a living process.
Okay, so here's the playbook for a really common and powerful type of MSA called a gauge R&R study. First, you figure out your data type. Then you select your inputs. Who's going to do the measuring? What parts are you going to use? And how many times will you repeat it? And this is critical. You have to use the normal operators and their normal procedures. We want to test the system as it actually runs. Next, you need to pick parts that represent the full range of what you produce, the good, the bad, and the ugly. And then, 2 final crucial steps. You mark the exact spot to be measured on each part, and then you completely randomize the order of measurements. Why? To prevent people from subconsciously remembering their last measurement and trying to match it.
So let's zoom out again. I know we've been deep in the statistical weeds, but it's so important to see that this isn't just some technical thing for the quality department. MSA is a core strategic capability. It's about building an organization that can actually trust what its own data is telling it. Look, if you're running Six Sigma projects, every single phase of DMAIC depends on this. If you have an ISO 9001 certification, it's literally a requirement. MSA is the bedrock. Without it, your data-driven culture is really just a guest-driven culture with really nice spreadsheets. So what's the benchmark? How good is good enough? Well, the Automotive Industry Action Group gives us a fantastic rule of thumb. If your measurement system is responsible for less than 10% of the total variation, you're in the green. You're good. Between 10 and 30%, it's a yellow light. It might be okay, but you should probably look into it. But if your measurement system itself is causing more than 30% of the variation you see, that's a 5-alarm fire. It is unacceptable, and you need to fix it now. So I'll end by turning this whole framework back on you and your organization. I want you to think about the critical KPIs that run your business. Your OEE, your customer SAT scores, your defect rates. Now that you have this new lens, accuracy, precision, repeatability, reproducibility, which one of those numbers makes you the most nervous? Which one, deep down, feels a little bit like a guess? Yeah, that one, that's your starting point. Go fix it.